Andromeda is already touching us. Not with stars or light, but with something we cannot see, a sea of gas stretching more than 1 million light-years from its heart. It has already reached halfway across the space that separates our galaxies. The collision everyone thought would happen billions of years in the future has already begun, quietly, in the dark. For centuries, humanity looked at Andromeda and saw only a smudge in the night sky. A faint blur between Cassiopeia and Perseus, visible on clear autumn nights. We thought it was small. We thought it was distant. We thought it was another object in the endless sky. But the truth is larger, heavier, and closer than we ever imagined. Through the eyes of modern telescopes, the illusion has been stripped away. The galaxy that seems calm to the naked eye is a vast structure of stars, gas, and dark matter bound together by gravity. It is not a separate world, isolated and serene. It is part of the same story that made our own Milky Way. Every particle of light that leaves its stars travels 2.5 million years before it reaches us. And yet, on that scale, Andromeda is practically next door. For decades, astronomers believed they had mapped its edges. They drew neat boundaries where the faint glow faded into the black. But those edges were never real. They were limits of our vision, not of the galaxy itself. Today, the evidence shows that Andromeda is not just another island of stars. It is a continent of gravity whose invisible atmosphere already collides with ours. This story is not speculation. It is built on measurement. The numbers, the wavelengths, the spectra that reveal what our eyes cannot. It is a story about discovery, about how a familiar blur in the sky became the key to understanding how galaxies live, breathe, and evolve. The deeper astronomers looked, the more Andromeda expanded. They found its halo, a sphere of superheated plasma, and with it, a revelation. The galaxy we thought we knew was twice as large, twice as massive, and far more alive than anyone expected. And somewhere within that vast system, our own galaxy is already connected to it, bound by threads of gas and gravity that stretch across millions of light-years. The Andromeda Galaxy, also known as M31, is not waiting for the future. It is already part of ours. It does not sit silently at a distance. Its presence fills the night sky, though our eyes are too limited to see it. If we could view it in full, it would dominate the heavens, a glowing spiral wider than any constellation, dwarfing the moon, stretching from horizon to horizon. This is where the story begins, with a familiar neighbor that turned out to be far larger than we ever believed. A galaxy so immense that its edge is already brushing against our own. A reminder that in the universe, nothing stands still, and even across the vastest distances, everything is connected. For most of modern astronomy, Andromeda appeared to end where its light faded. The faint spiral we saw through telescopes seemed complete, a glowing disk of stars surrounded by darkness. But in 2015, the Hubble Space Telescope revealed that the visible galaxy was only a fraction of its true size. Beyond the glowing spiral arms, beyond the thin veil of faint starlight, stretches a massive envelope of invisible matter, a halo so vast that it changes everything we thought we knew about our closest galactic neighbor. The discovery began with an international research project called OMEGA, the absorption map of ionized gas in Andromeda. Its goal was simple in theory but revolutionary in practice. Instead of photographing the galaxy, astronomers used it as a lens, a filter placed between Earth and the distant universe. They studied 43 quasars positioned behind Andromeda. Each quasar is powered by a supermassive black hole billions of light-years away, releasing intense light that crosses the cosmos long before reaching us. As that light passed through Andromeda's outer regions, it carried a signature, small, precise fingerprints of gas hidden in the void. Hubble's Cosmic Origins spectrograph detected tiny drops in brightness at specific wavelengths. Each drop represented absorption by particular elements, oxygen, carbon, silicon, nitrogen, all suspended in a sea of plasma surrounding the galaxy. By analyzing those patterns, astronomers could map the invisible. They could measure how far this gas extended, how dense it was, and what it was made of. The results were staggering. Andromeda's halo stretches 1.3 million light-years from its center. In certain directions, it extends as far as 2 million. That means if human eyes were sensitive to ultraviolet light, the Andromeda galaxy would not appear as a faint smudge in the sky. It would fill nearly a quarter of the heavens, larger than the Big Dipper, wider than any constellation. The largest visible feature in the entire night sky would not be the Milky Way. It would be Andromeda. This halo is not made of stars or planets. It is a vast, diffuse atmosphere composed of ionized gas, plasma so thin that each cubic meter contains only a few atoms, yet heated to hundreds of thousands of degrees. It does not glow visibly, but it absorbs specific bands of ultraviolet light. That is how astronomers found it, not by seeing its glow, but by detecting the light it stole. The mass of this halo was another surprise. It contains nearly as much material as half of all the stars inside Andromeda's disk. In cosmic terms, that means the space between the stars is not empty. It is a living part of the galaxy itself, a vast reservoir from which new stars will someday form. The halo acts like a breathing system, recycling material ejected by dying stars and returning it to fuel the birth of the next generation. The scale of it challenges intuition. 1 light-year equals nearly 6 trillion miles. The halo extends for more than 1 million of those light-years in every direction. It is so large that it already reaches halfway toward us. And because the Milky Way has a similar halo, the two are not truly separate anymore. They have already met. Our galaxies are connected right now through an invisible bridge of hot, ionized gas stretching across intergalactic space. This realization changed the story entirely. The collision between Andromeda and the Milky Way, once thought to be a distant event billions of years away, is not something waiting to happen. It has already begun. Not with stars colliding or black holes merging, but with atoms, protons, and electrons drifting between two gravitational giants. The first contact is silent, but it is real. Every year, new data confirms it. Scientists studying this halo also discovered that it is layered, like the atmosphere of a planet. An inner shell, denser and more metal-rich, surrounds the galaxy's disk. Beyond it lies a second, thinner layer stretching into the void. Each layer tells a part of Andromeda's history. Over billions of years, the galaxy has consumed smaller neighbors, dwarf galaxies pulled in by gravity, their stars and gas torn apart and mixed into Andromeda's outer regions. Every collision left a trace, a chemical scar preserved in the halo's composition. These layers are not uniform. Some regions contain high concentrations of oxygen and carbon, evidence of ancient supernovae that enriched the gas with heavy elements. Other regions are cleaner, more primitive, closer to the raw hydrogen that filled the universe after the Big Bang. The pattern reveals the rhythm of Andromeda's life cycle. It forms stars, they die, they explode, and their ashes spread outward, becoming part of the halo. Over time, gravity pulls some of that material back toward the disk, where it becomes the raw material for new stars. The galaxy breathes, inhaling and exhaling across cosmic time. Even more striking is what this means for us. If the halos of both galaxies overlap, then the Milky Way is no longer isolated either. Material from Andromeda is already mixing with material from our own halo. Atoms that once belonged to distant stars could someday end up in future generations of our solar system. In the vast emptiness of space, galaxies are not separate islands. They are connected ecosystems sharing matter, energy, and history. The Omega project was not the end. It was the beginning of a new understanding of galactic structure. Subsequent research using the Hubble Space Telescope, the Cosmic Origin Spectrograph, and other observatories confirmed the finding again and again. They found that halos like this are common. Most large galaxies have them, but Andromeda's is special because of its proximity. It is the only one close enough to study in such detail. Through Andromeda, we see a reflection of ourselves. Its shape, its size, its chemistry, all mirror the Milky Way's own structure. By studying its halo, we learn what our own must look like from the outside. And what we find is humbling. The borders between galaxies are not sharp. They fade into one another, overlapping like tides in an ocean without shores. So when we look at the faint light of Andromeda through a telescope, We are not seeing a distant object separated from us by millions of years. We are looking through the first bridge that connects two galaxies. The future collision has already started, not with chaos or destruction, but with the quiet exchange of gas and gravity that binds the universe together. To understand Andromeda, we must first grasp its scale, a task almost impossible for the human mind. Even the word large fails here. Andromeda is not just wide, it is immense beyond comparison. When we talk about galaxies, we talk in units of light years. The distance light travels in a year, nearly 6 trillion miles. Andromeda spans about 200,000 of those light years across its visible disk. That alone makes it twice the diameter of the Milky Way. But that is only the visible part. When the hidden halo is included, the true diameter stretches close to 2 million light-years from edge to edge. At that scale, every detail becomes extraordinary. Each spiral arm contains hundreds of billions of stars. The central bulge, glowing golden with age, holds the oldest populations, ancient red giants and dying suns that have burned for 10 billion years. Toward the outer regions, younger blue stars dominate, massive and bright, living fast and dying in spectacular explosions. This color gradient is not decoration, it is a timeline. The center tells the story of Andromeda's past, while the spiral arms record its present. Every shade of light marks an age, a cycle of birth and death written in starlight. Astronomers estimate that Andromeda contains roughly 1 trillion stars. That number is so large that it defies visualization. If you counted one star every second, never sleeping, it would take more than 30,000 years to reach the end. And each of those stars is not a point of light but a system, many with planets, moons, asteroids, and perhaps the raw ingredients for life. Andromeda is not one world. It is a trillion separate stories unfolding together. When NASA's Hubble Space Telescope captured the most detailed image ever taken of an external galaxy, it was Andromeda. The project was called the Panchromatic Hubble Andromeda Treasury, or FAT. It required more than 400 individual pointings of the telescope between 2010 and 2013, producing over 7,000 separate exposures. When all the frames were combined, the result was a mosaic containing 1.5 billion pixels. Inside that single image, scientists could identify more than 100 million individual stars, each one mapped, measured, and catalogued. No other galaxy beyond our own has ever been seen in such detail. Looking at the FAT image is like looking at time itself. The light captured by Hubble began its journey 2.5 million years ago. When that light left Andromeda, the earliest humans on Earth were just learning to shape stone tools. The light crossed the intergalactic void, passed through invisible halos of gas, and finally entered the mirrors of a telescope orbiting above Earth. Each pixel of that image is not only data. It is history, an ancient signal arriving from the past. In those photographs, astronomers could see how stars are arranged, how dust weaves through the spiral arms, and how different regions tell different stories. The spiral arms are lined with glowing hydrogen clouds, the places where stars are born. These clouds collapse under gravity, heating until nuclear fusion ignites at their cores. Every year, Andromeda produces new stars equal in mass to our own sun. This rate may seem slow, but over cosmic time, it builds entire generations of stellar systems. Between those bright regions lie the dust lanes, dark threads that absorb visible light but glow in the infrared. Infrared observations from NASA's Spitzer Space Telescope revealed these filaments in detail. They are composed of microscopic grains of carbon, silicon, and ice. They mark the raw material of creation, the matter that will someday form new stars, planets, and maybe life itself. Seen in visible light, these regions appear as shadows. Seen in infrared, they are the beating heart of the galaxy's future. At the core of Andromeda sits its bulge, a dense sphere containing hundreds of billions of old stars packed tightly together. Here, distances between stars shrink dramatically. If Earth orbited inside that region, the night sky would never be dark. Thousands of suns would shine brighter than Venus, filling the heavens with unending daylight. These stars are ancient survivors, the remnants of the galaxy's earliest generations. Their light is dimmer, their temperatures cooler, their lives slower. They orbit the center like bees around a hive, tracing the gravitational influence of something immense and unseen, the supermassive black hole that anchors the entire system. The contrast between the calm center and the restless arms defines Andromeda's structure. The central bulge rotates slowly, its stars following random paths. The disk, by contrast, spins in near-perfect order. Each star follows an orbit hundreds of millions of years long around the galactic center. One complete rotation of the disk takes roughly 240 million years. That means Andromeda has only made about 40 full rotations since it first formed over 10 billion years ago. Dark matter adds another layer to this structure. Although invisible, it makes up most of the galaxy's total mass. The stars, gas, and dust we can see account for only a fraction. The rest is hidden in a massive dark halo that extends far beyond the visible edge. This unseen matter provides the gravity that holds the galaxy together. Without it, the stars in the outer arms would fly off into space. Instead, they move as if bound by a silent hand. Through gravitational studies, scientists estimate Andromeda's total mass, including dark matter, at roughly 800 billion times that of our Sun. The Milky Way, once believed to be smaller, has since been found to be heavier, around 1.5 trillion solar masses. This means our galaxy has more dark matter, while Andromeda has more visible light. It is as if one hides its strength beneath the surface while the other shines brightly above it. Together, they balance each other, one luminous, one massive, drawn together by mutual gravity. But Andromeda is not static. Its stars are not fixed points in a photograph. They move, they collide, they orbit, and they evolve. Some are born in clusters, hundreds forming together within vast clouds of hydrogen. Over time, those clusters drift apart as stars age and scatter across the disk. Others form alone, wandering between the arms, their light faint but enduring. Each star contributes to the galaxy's overall rhythm, like notes in an endless cosmic symphony. Even from 2.5 million light-years away, Andromeda dominates our sky. Its visible disk spans 3 degrees, 6 times wider than the full moon. Under perfectly dark skies, the human eye can just glimpse it, a pale oval of light with a bright center fading into shadow. That faint blur is a direct look into another galaxy, a neighbor so close that astronomers call it part of our local group. A small collection of about 100 galaxies bound together by gravity. Among them, Andromeda and the Milky Way are the two giants, each shaping the destiny of the smaller ones around them. Andromeda's structure is not just a collection of stars. It is a record of cosmic evolution. Its layers reveal when it formed, how it grew, and what it has consumed. Every ring of light, every dust lane, every cluster is a page in a story billions of years old. And through telescopes and data, we are finally learning to read it. And yet, all of this, the disk, the arms, the bulge, the halo, is only part of the story. Because Andromeda's calm spiral hides evidence of violence, of collisions and mergers that shaped everything we see today. To understand the galaxy we face across space, we must first understand what it has already survived. The calm, perfect spiral of Andromeda hides a violent past. Every galaxy carries scars, and this one is no exception. Behind the symmetry of its glowing arms lies a history of destruction, mergers, collisions, and cannibalized neighbors that reshaped it into what we see today. Astronomers call it a fossil record written in stars. Between 2 and 3 billion years ago, something enormous happened. Andromeda collided with another galaxy. It was not a gentle meeting. The smaller system was roughly 1/4 of Andromeda's mass, large enough to tear through its disk and disturb its structure for billions of years to come. The impact was so powerful that it triggered one of the most intense bursts of star formation in the galaxy's history. When galaxies collide, their stars almost never strike each other directly. The space between them is too vast. But their clouds of gas and dust do collide, compressing under shock waves and gravity. The result is chaos, a storm of creation. For nearly 100 million years after that ancient collision, Andromeda became what astronomers call a luminous infrared galaxy. Star formation rates jumped to nearly 100 times higher than normal. Thousands of massive blue stars were born every year. The entire galaxy glowed brighter than ever before. The evidence of this event is everywhere once you know how to look. Spectroscopic studies reveal that many of Andromeda's stars are about 2 billion years old, all formed around the same time. They move differently from the older populations, their orbits tilted and uneven. These strange motions make sense only if they were born in a turbulent, collapsing disk after a violent merger. Other clues come from Andromeda's structure itself. Its disk is unusually thick, broader and puffier than most spirals of similar size. Computer simulations show that such thick disks form when a galaxy absorbs a smaller companion. The collision stirs the stars and gas, throwing some upward and downward from the galactic plane. When everything settles again, the disk no longer lies flat. It bulges with the memory of impact. The galaxy's rings tell the same story. When viewed in ultraviolet light, Andromeda's elegant spiral pattern dissolves, revealing a series of bright concentric rings surrounding the core. Each ring marks a wave of star formation triggered by the ancient collision. Imagine dropping a stone into a still pond. Ripples spread outward in circles. In a galaxy, those ripples are density waves, compressions of gas that move across the disk, igniting new stars as they go. NASA's Galaxy Evolution Explorer, or GALEX, captured these ultraviolet rings in exquisite detail. They shine with the blue-white light of young, massive stars, a silent echo of the event that created them. Some astronomers believe those rings may also have been shaped by a later encounter with one of Andromeda's smaller companions, possibly M32. Simulations show that if a small galaxy like M32 passed directly through Andromeda's disk about 200 million years ago, it could have created another set of ripples, refreshing the pattern we see today. Whether the rings came from one impact or several, they are undeniable evidence that Andromeda's past was anything but peaceful. The scars of those encounters reach far beyond the visible disk. In the galaxy's outer halo, astronomers have found long, faint streams of stars stretching hundreds of thousands of light years. These are tidal tails, remnants of smaller galaxies pulled apart by Andromeda's gravity. Each stream marks the orbit of a victim slowly being devoured. The Pan-Andromeda Archaeological Survey mapped many of these features, uncovering dozens of faint satellite galaxies and debris fields. Together, they form a kind of galactic graveyard orbiting the main spiral. These streams also explain the chemical composition of Andromeda's halo. The gas there is rich in heavy elements like oxygen and iron, materials forged in supernova explosions. Such enrichment can only occur when a galaxy goes through waves of star formation and destruction. Each merger feeds that process. New stars form from the gas, they live and die, and their deaths fill the halo with metals. Andromeda's halo today is a mixture of its own material and the remains of everything it has consumed. Astronomers can even estimate how many mergers Andromeda has experienced. By comparing its current structure to computer models, they conclude that it has swallowed at least a dozen dwarf galaxies over the past 10 billion years, and possibly many more. Some were small, barely containing a few million stars. Others were large enough to alter Andromeda's entire shape. The merger that occurred 2 to 3 billion years ago was likely the largest in recent history, the event that defined the modern Andromeda we see today. That collision also explains the distribution of ages among Andromeda's stars. In its central regions, the average star is older than 7 billion years. In the outer disk, the average drops to 2 billion. This gradient matches what you would expect if the galaxy underwent a massive burst of star formation after merging with a smaller system. The center remains stable, but the outer regions lit up with new life. The evidence does not end there. The halo surrounding Andromeda is not smooth. It is filled with substructures, clumps, filaments, and loops of gas that mark ancient accretion events. Each of those fragments once belonged to another galaxy. Over billions of years, Andromeda's gravity tore them apart and scattered their remains across its outskirts. Today, that debris forms faint arcs visible only in deep surveys. They are the fingerprints of the galaxies that came before. This process of galactic growth is not unusual. It is how most large galaxies evolve. They grow by devouring smaller ones. Gravity brings them together, and over time, the smaller system is stretched, shredded, and absorbed. What makes Andromeda special is how clearly we can see the evidence. Because it is so close, astronomers can study its stars individually, tracing their motions and chemical makeup to reconstruct the events of the past. The story that emerges is one of constant transformation. Andromeda was not born as we see it now. It was built piece by piece, through a chain of collisions stretching back to the early universe. Every orbiting star, every ring, every stream of light carries the memory of those impacts. Its elegant spiral form is not the result of calm creation but of violent balance, chaos settled by gravity into order. And even now, that process continues. Andromeda is not finished consuming its neighbors. The small galaxy known as M32 is being stripped of its outer layers. Another, M110, is slowly being stretched into an elongated shape. Over millions of years, both will be reduced to fragments and drawn into the main disk. In time, they too will disappear, leaving behind nothing but tidal debris and a richer halo. When we look at Andromeda's glowing arms, we are looking at the aftermath of countless acts of cosmic cannibalism. The beauty we see today was built on destruction. Its calm light is the final echo of ancient violence. And those same forces that shaped Andromeda's past are already shaping its future. Because even now, it is moving, slowly but surely, toward us. Andromeda is not drifting quietly through space. It is moving with purpose. Across the dark expanse between galaxies, it is closing the distance toward us at more than 100 kilometers every second. That is 240,000 miles per hour, fast enough to circle Earth 10 times in a single hour. Every second, the space between our galaxies shrinks a little more. This motion was first detected more than a century ago. In 1912, at Lowell Observatory in Arizona, astronomer Vesto Slipher pointed a spectrograph toward the faint spiral of Andromeda. What he found was unexpected. The dark absorption lines in the galaxy's light spectrum were shifted toward the blue end, evidence that it was moving toward, not away from, the Milky Way. Until then, most known galaxies showed red shifts, signals of an expanding universe carrying them outward. Andromeda was different. It was coming closer. At the time, few understood what that meant. Even the word galaxy had not yet taken its modern meaning. Many astronomers still believed Andromeda was a small nebula inside our own Milky Way. Only years later, after Edwin Hubble measured the distances to spiral nebulae, did we realize these were separate island universes, vast systems of stars far beyond our own. Once that was known, Slipher's discovery became far more dramatic. Two galaxies, each hundreds of billions of stars strong, were on a collision course. Modern instruments have refined those early measurements. Today we know Andromeda is roughly 2.5 million light-years away and moving toward us at about 110 kilometers per second. In cosmic terms, that is not an enormous speed. But over billions of years, it is more than enough to bring two galaxies together. The question has always been not whether they are moving closer, but whether they will actually collide. For decades, scientists assumed the answer was yes. Simulations predicted that the Milky Way and Andromeda would meet head-on about 4 billion years from now, merge completely after a series of slow gravitational encounters, and form a single giant elliptical galaxy. That scenario even earned a name, Milkomeda, or sometimes Milkdromeda. Textbooks, documentaries, and planetarium shows presented the event as inevitable. Then new data changed everything. In 2012, astronomers using the Hubble Space Telescope measured Andromeda's proper motion, its sideways drift across the sky. They compared the positions of thousands of stars against distant background galaxies over an 8-year baseline. The results surprised everyone. Andromeda's sideways motion was almost zero. The galaxy was heading almost directly toward us, confirming a collision seemed certain. But science never stops testing its own certainty. A decade later, the European Space Agency's Gaia mission added an even more precise layer of information. Gaia measures the positions and motions of more than 1 billion stars in our galaxy with microarcsecond accuracy, the equivalent of tracking the width of a coin on the moon. When combined with Hubble's Andromeda data, scientists could calculate the gravitational influences of every major neighbor in our local group, not just the 2 main spirals. The new picture that emerged was far more complicated and far less certain. In 2025, a team led by astrophysicist Timo Saila at the University of Helsinki published a sweeping statistical study in Nature Astronomy. They ran 100,000 computer simulations, each one varying the masses, velocities, and positions of every significant galaxy in the local group within their measurement uncertainties. They also included the gravitational effects of 2 smaller but critical players, the Triangulum galaxy, known as M33, which orbits Andromeda, and the Large Magellanic Cloud, a satellite of the Milky Way. What they found overturned a decade of certainty. Depending on the exact parameters, there is roughly a 50% chance the Milky Way and Andromeda will collide and merge within the next 10 billion years, and a 50% chance they will not collide at all. Our cosmic future, once presented as a fixed destiny, has become a coin toss. The reason lies in those smaller companions. Triangulum exerts a steady gravitational pull on Andromeda, subtly tugging it toward the Milky Way. Left alone, that influence would make a merger almost guaranteed. But the Large Magellanic Cloud complicates the picture. It orbits our galaxy on a tilted, nearly perpendicular path and carries about 15% of the Milky Way's total mass. As it swings around us, it pulls the Milky Way sideways, shifting our trajectory just enough to change the outcome. Imagine 2 ships drifting toward each other across a calm sea. A small tugboat nudges one of them, only slightly, but continuously. Given enough time, that gentle push can make them miss by miles. The Magellanic Cloud is that tugboat. Over millions of years, its steady gravitational pressure may deflect the Milky Way just enough for Andromeda to pass by instead of colliding. This revelation does not mean the 2 galaxies will remain strangers. Their halos are already touching, and that interaction will continue no matter what happens to the visible disks. Gas will flow between them, magnetic fields will intertwine, and smaller satellite galaxies will have their orbits disturbed. But a near miss, even by a few 100,000 light-years, would spare both systems the full violence of a merger. If the collision does occur, it will unfold slowly. Nothing about it will resemble an explosion. Galaxies are mostly empty space. When they meet, stars pass by one another without contact. The drama happens in their gas clouds and in their shapes. Gravitational tides stretch them into long arcs, flinging streams of stars into intergalactic space. Each close pass triggers new waves of star formation as gas clouds collide and compress. Over billions of years, repeated encounters erase the spiral structure, leaving behind a rounded, featureless elliptical galaxy glowing with the light of aging stars. Even if the galaxies miss each other this time, gravity will not let them rest forever. Other members of the local group, the Triangulum galaxy, the Magellanic Clouds, and dozens of dwarf systems, all tug on one another in a complex dance. Eventually, interactions among them will reshape everything again. In the distant future, the local group will collapse into a single massive system, bound together while the wider universe continues expanding. For now, the numbers keep changing. Each new mission, each improved measurement adds precision to the story. The Gaia spacecraft continues to collect data, refining our understanding of the Milky Way's motion through space. Future observatories, such as the Nancy Grace Roman Space Telescope, will push that accuracy even further, possibly revealing whether the collision is certain or avoidable. But even uncertainty carries beauty. The fate of 2 galaxies, each containing hundreds of billions of stars, may depend on the influence of one small satellite galaxy, a reminder that in the universe, size does not always dictate consequence. Tiny objects can decide the futures of giants. Whatever the outcome, the early stages of interaction are already underway. Gas from both halos is mixing. Gravitational tides are shaping the orbits of satellite galaxies. In slow motion, the prelude to a cosmic meeting has begun. When you look at Andromeda on a dark night, you are seeing the future as well as the past. The light reaching your eyes began its journey 2.5 million years ago, but the motion it reveals is ongoing right now. Every second that passes brings our galaxies closer together by another 100 kilometers. Across that vast distance, gravity is writing the next chapter of our shared story, one that will unfold over billions of years, long after our sun and our world are gone. The collision, whether it happens or not, reminds us that nothing in the universe is truly still. Even on cosmic scales, everything moves, everything evolves, and every galaxy carries the momentum of its creation. The Andromeda galaxy is not just approaching us. It is calling us into the next phase of the universe's grand design. Long before any star from the Milky Way meets a star from Andromeda, their outermost atmospheres have already touched. This first contact does not flash or explode. It happens silently, through the slow diffusion of gas and the steady pull of gravity across intergalactic space. Every large galaxy is surrounded by a vast halo, an invisible sphere of hot plasma, magnetic fields, and dark matter extending far beyond its visible stars. In the case of Andromeda, that halo stretches more than 1 million light-years from its center. The Milky Way's halo is roughly the same size. The two have expanded and now overlap, blending in a region of shared gas and energy halfway between both galaxies. That overlap is the first stage of a merger, the meeting of atmospheres before the meeting of bodies. The temperature inside these halos reaches hundreds of thousands of degrees, but the gas is incredibly thin. Each cubic meter contains only a few atoms, scattered like dust in a cathedral of emptiness. Yet because the volume is so large, the total mass of this material rivals that of all the stars in either galaxy. The halos act like enormous ecosystems, recycling matter between the galaxies and the space around them. Astronomers detect this invisible substance through absorption lines in ultraviolet light. When light from distant quasars passes through the halos, certain wavelengths are absorbed by the ions suspended in the gas. These signatures tell scientists what the halos are made of and how they move. By comparing the spectral fingerprints of the Milky Way's halo to those of Andromeda, they can see the blending point, a faint region where both signatures appear together. It is the borderless edge where the two atmospheres mix. In that region, gravity and magnetism interact in ways we can only partially understand. Plasma filaments, strands of charged gas stretching for hundreds of thousands of light years, thread through both halos. They carry magnetic fields that twist and merge, transferring energy much like the lines of force between two stars. Where these filaments meet, they can create localized turbulence, slow whirlpools of gas that heat the surrounding medium even more. This gradual entanglement has consequences. The halos act as regulators for star formation within the galaxies. They control how gas flows in and out of the disks. When the two halos merge, those flows begin to change. Some regions experience compression, feeding new bursts of star formation. Others experience stripping, where gas is pulled away and lost to intergalactic space. Over millions of years, this interaction will alter the balance of both galaxies long before the main bodies collide. The merging halos also serve as a laboratory for studying cosmic magnetism. Magnetic fields on such scales are difficult to measure, but their presence is undeniable. Observations of polarized radio waves show subtle distortions that can only be explained by magnetized plasma. When two halos overlap, those fields begin to reconnect, releasing energy in a slow but powerful process similar to what happens on the surface of the Sun. Except here, the stage is measured in light years instead of kilometers. Inside this vast contact zone, tiny galaxies and star clusters drift like seeds in a cosmic wind. Many of them belong to the outer systems of Andromeda or the Milky Way, dwarf galaxies too small to resist the pull of either giant. Some will be captured and drawn inward, joining the growing list of satellites already orbiting the two main galaxies. Others will be stripped of their gas and left behind as faint stellar skeletons, reminders of the tides that move between galaxies. The first direct observational evidence of this overlap came from the Hubble Space Telescope's Cosmic Origins spectrograph. Researchers found that the gas surrounding Andromeda and the Milky Way shared similar temperatures, ionization states, and metallicity levels in the space between them. These shared properties are not random coincidences. They indicate that the two halos have begun exchanging material. Atoms that once belonged to one galaxy now drift freely in the space of the other. In essence, the merger has already started, not in the visible spectrum, but in ultraviolet and X-ray wavelengths. It is a merger of energy before matter, a handshake of atmospheres across a gulf of emptiness. This quiet process may continue for hundreds of millions of years before anything visible changes in the night sky. But in the language of astronomy, it has already rewritten our understanding of the Milky Way's environment. Simulations show that as the halos continue to blend, the region of interaction will grow denser. Pockets of gas may cool and condense, forming isolated clouds that could one day ignite new stars far outside the traditional boundaries of either galaxy. Others will heat up, energized by magnetic friction, and escape as intergalactic winds. These opposing forces, creation and dispersal, mark the balance of galactic life. Every collision, every merger, follows this pattern. New stars are born even as old structures dissolve. To visualize this process, imagine two soap bubbles drifting toward each other. At first, only the thinnest film between them meets. Then, as pressure equalizes, their surfaces deform and the bubbles begin to merge. Eventually, they form a single, larger bubble. Galactic halos behave much the same way, except their surfaces are invisible, their gases are ionized, and the timescales are millions of years long. Astronomers refer to this moment, the point of initial overlap, as the onset of coalescence. It is the beginning of a cosmic process that will eventually bind the Milky Way and Andromeda into a shared gravitational structure. At present, they remain distinct entities, each with its own spiral disk and central black hole. But in the region between, identity fades. The space that once separated them is now part of both. Over time, as the galaxies move closer, this connection will strengthen. Streams of gas will begin to flow more freely between the two. Some may fall inward, fueling new star formation near the galactic centers. Other streams may be pulled outward, creating bridges of material that stretch across the void. These bridges are not visible to the human eye, but radio telescopes and space-based observatories can trace them by their faint emissions. The merging halos also exert subtle influences on the stars within each galaxy. Their combined gravitational field slightly alters stellar orbits at the edges of the disks. In the outer reaches of the Milky Way, stars are already moving under the faint tug of Andromeda's mass. It is a reminder that even across millions of light years, gravity never sleeps. This phase, the halo merger, is the universe at its most understated. No supernovae, no fireworks, no collisions of stars. Just slow, continuous blending. Yet, on cosmic scales, it is one of the most important steps in galactic evolution. It sets the stage for everything that will follow, the deformation of disks, the tidal bridges of stars, and eventually, the merging of black holes at the centers. By the time the visible collision begins billions of years from now, the groundwork will already have been laid by these halos. Their mixing ensures that when the galaxies finally touch, their gases and magnetic fields will already be intertwined. The first contact has already taken place, not in light, but in silence. If the Milky Way and Andromeda stay on their present course, gravity will one day erase the distance between them. It will not happen in our lifetime or in the lifetime of our world. The estimated time of first physical contact is about 4 billion years from now. On cosmic scales, that is soon. The galaxies will not meet as solid objects. They will approach like two clouds passing through each other. Each cloud holds hundreds of billions of stars, yet the space between those stars is enormous. The odds of any two stars colliding are almost zero, but gravity will shape every motion, pulling and stretching both systems into new forms. Astronomers simulate this event using supercomputers that model the gravitational forces between individual particles of mass. Each simulation begins with the known positions, velocities, and masses of both galaxies, then runs forward through time. The result is a slow, beautiful dance of distortion. As the galaxies near each other, their disks start to warp. Spiral arms twist into long tidal tails, streams of stars flung outward like ribbons of light. Gas clouds compress where the disks overlap, igniting intense waves of star formation. These temporary outbursts will give birth to new generations of brilliant, short-lived blue stars that burn intensely before dying in supernovae. The first pass will last hundreds of millions of years. Andromeda will sweep through the Milky Way, dragging a trail of stars behind it. Both galaxies will recoil, slowed but not stopped. Gravity will pull them back together again for a second pass, then a third. With each encounter, more of their material will mix. Their once distinct disks will lose shape, replaced by an expanding, glowing cloud of stars. Eventually, friction within the gas and dark matter halos will drain away the remaining energy of motion. The two systems will settle into one. The final product will not be a spiral galaxy. It will be an elliptical, a smooth, featureless sphere of light. Spiral structure cannot survive a merger of equals. The orderly rotation of the disks is disrupted, replaced by random, three-dimensional orbits. The result will be a galaxy perhaps twice the size of either parent, glowing with the light of 1 trillion stars. Astronomers have even given it a name, Milkomeda, the galaxy that will someday replace both the Milky Way and Andromeda. Inside that new galaxy, the Sun, if it still exists, will find itself in an unfamiliar sky. By that time, our star will be near the end of its life. It will have expanded into a red giant and shed its outer layers, leaving behind a small white dwarf remnant. Whatever planets remain will orbit in darkness, surrounded by millions of unfamiliar suns. The night sky will no longer be a thin band of stars. It will be filled in every direction with light, far denser and brighter than today. Computer simulations allow us to see this distant future in remarkable detail. The most famous of these, created by NASA's Goddard Space Flight Center, shows the entire process in slow motion. At first, the Milky Way's spiral arms begin to distort. Then a glowing front of new stars erupts as the galaxies make their first pass. Over the next few billion years, the two systems loop around one another, their cores drawing closer with each cycle. Finally, their central regions fuse, and the new elliptical galaxy stabilizes. Viewed from within, the process would be spectacular yet slow. A sky filled with arcs, streams, and clouds of stars shifting over millions of years. At the center of the merged galaxy, two supermassive black holes will meet. The Milky Way's black hole, known as Sagittarius A*, has a mass of about 4 million suns. Andromeda's central black hole is far larger, roughly 100 million solar masses. When the galaxies combine, these black holes will begin orbiting one another, gradually spiraling inward. As they draw closer, they will emit gravitational waves, ripples in the fabric of space-time first predicted by Einstein and now routinely detected by instruments such as LIGO and Virgo. The final merger will release more energy in gravitational radiation than all the stars in the new galaxy emit in light during that moment. Yet, to anyone living far away, the event will be silent and invisible. After the black holes merge, the new core will settle, and the galaxy will become stable again. Gas reserves will slowly decline as star formation consumes what remains. Over billions of years, the young blue stars will die, replaced by long-lived red dwarfs. The once bright galaxy will fade to a gentle orange glow. Milkomeda will remain massive and majestic, but quieter, a city of aging stars coasting through cosmic twilight. This fate is not unique. Across the universe, similar mergers happen constantly. Large galaxies grow by consuming smaller ones, and when equals meet, they reshape each other entirely. Astronomers studying distant ellipticals can see snapshots of this process frozen in time. Some show twin cores in their centers, others display long tidal tails, all evidence of past collisions. By observing them, we glimpse what awaits our own system. Still, there are alternative outcomes. If the Large Magellanic Cloud deflects the Milky Way's path enough, Andromeda might pass by instead of colliding directly. In that case, Both galaxies would remain mostly intact but would influence each other profoundly. Their halos would fully merge, and their shapes would distort under tidal forces. Stars would be exchanged, and smaller companions would be thrown into new orbits. They would continue drifting together as a binary pair bound by gravity, locked in an endless slow dance. Either path leads to the same final chapter. Over trillions of years, the expansion of the universe will isolate the local group from the rest of the cosmos. Distant galaxies will recede beyond the reach of light. The Milky Way, Andromeda, Triangulum, and their satellites will remain bound together, forming a single massive system surrounded by darkness. Long after the stars within have dimmed, their shared gravity will persist. From a human perspective, these timescales are beyond imagination. Yet they remind us of an essential truth: galaxies are not static islands. They are evolving structures, alive in their own slow rhythm. The Andromeda merger is not a singular event but a continuation of that rhythm, the next heartbeat in a history that began when the universe was young. The future merger is also a mirror of the past. The same forces that built Andromeda through earlier collisions will one day reshape us both. It is the universe's way of recycling matter, energy, and motion. Nothing is lost, only transformed. When the Milky Way and Andromeda finally become one, there will be no explosion to mark the end, no boundary to cross. The change will come gradually, star by star, orbit by orbit. And when it is complete, the two great spirals that once faced each other across the void will exist only as memory, their remnants shining together in a new, unified light. At the heart of every large galaxy lies a gravitational engine, a supermassive black hole. Andromeda is no exception. Buried deep within its bright central bulge, hidden behind dust and layers of ancient stars, lies one of the quiet giants of the local universe. It weighs about 100 million times the mass of our Sun. By comparison, the black hole at the center of the Milky Way, Sagittarius A*, is only 4 million solar masses. If these two galaxies ever merge, Andromeda's black hole will dominate the new core. Yet despite its immense size, Andromeda's black hole is unusually faint. It emits only a fraction of the radiation we might expect from such a massive object. For decades, astronomers could not even confirm its presence. The central region of the galaxy appeared too calm, too dim. Only with the development of space-based observatories working in the infrared and X-ray spectra did the evidence become clear. The Hubble Space Telescope provided the first direct proof in the 1990s. By measuring the motion of stars near the core, astronomers detected velocities of several hundred kilometers per second, far too fast to be explained by visible matter alone. Only a dense, compact mass could produce such acceleration. That invisible mass, concentrated in a volume no larger than our solar system, revealed the black hole's existence. Closer inspection brought even more mystery. When Hubble's high-resolution camera zoomed in on Andromeda's nucleus, it did not reveal a single point of light, as expected. Instead, it showed two distinct peaks, labeled P1 and P2. At first glance, they looked like two separate clusters of stars orbiting side by side. Later analysis showed that these two bright spots are part of one structure, a disk of stars orbiting the central black hole in an elongated ellipse. From our vantage point, the stars are moving at different angles, creating the illusion of a double nucleus. In the early 2000s, NASA's Spitzer Space Telescope observed the region in infrared light and confirmed the same structure. The two bright concentrations are regions where dense clusters of stars orbit near the black hole, their paths twisted by gravity into a disk just a few light years across. This disk likely formed when gas fell toward the center, fragmented, and condensed into stars. These are among the most gravitationally bound stars known, trapped in orbits that take only a few hundred years to complete. The central black hole itself, designated M31*, is classified as a low-luminosity active galactic nucleus. It accretes material from its surroundings at a very low rate, producing a weak but detectable signal in radio and X-ray wavelengths. Observations from NASA's Chandra X-ray Observatory show faint flares every few months, bursts of radiation lasting several hours before fading again. Each flare represents a small amount of gas or dust being swallowed by the black hole. The energy released during these moments would equal millions of times the power output of our sun, yet from the scale of an entire galaxy, it is only a flicker. This quiet state contrasts sharply with the violent activity seen in more distant galaxies. In quasars and active nuclei, supermassive black holes consume matter at furious rates, shining brighter than all their host galaxies combined. Andromeda's black hole, by comparison, is dormant, a sleeping giant that feeds only occasionally. Its calm nature allows the surrounding region to remain stable, giving astronomers a rare view of what such an object looks like in its resting phase. The behavior of M31* also provides clues about Andromeda's history. During its ancient merger 2 or 3 billion years ago, vast amounts of gas would have fallen toward the center. That inflow likely fueled a brief period of activity, turning the black hole into a powerful quasar for a short time. Once the available material was consumed or blown away by radiation pressure, the engine went silent again. The faint X-ray glow we see today is the last echo of that active past. Around the core, astronomers have discovered a dense star cluster called P3. This cluster contains hot, young blue stars, an unusual find in such an environment. Stars that close to a black hole should be quickly disrupted by gravity, yet these appear newly formed. Their presence suggests that even now, occasional bursts of star formation occur near the event horizon. Gas trapped in orbit around the black hole can become dense enough to ignite new stars before being pulled inward. It is a cycle of destruction and creation happening on the edge of nothingness. As Andromeda and the Milky Way draw closer, their central black holes will begin to influence each other. The gravitational tides will disturb the flow of gas within both galaxies, channeling fresh material toward their cores. That inflow will reawaken the dormant giants. For a time, both M31* and Sagittarius A* may flare brightly again, each feeding on the new gas supply. When the galaxies finally merge, their black holes will orbit one another in a long, slow spiral lasting millions of years. Eventually, they will coalesce into one, releasing a final pulse of gravitational waves strong enough to ripple spacetime across millions of light years. For now, Andromeda's core remains a place of paradox. Intense gravity, yet relative peace. Immense power, yet near silence. Every observation reminds us that not all cosmic power reveals itself through violence. Sometimes, the most massive forces in the universe work quietly, shaping the galaxies around them without drawing attention. The study of M31* helps astronomers understand how galaxies evolve. Supermassive black holes and their host galaxies grow together, influencing each other in a feedback loop. When a black hole feeds actively, it releases winds and radiation that can push gas away, halting star formation. When it goes quiet, the gas cools and new stars begin to form again. This alternating rhythm controls a galaxy's life cycle over billions of years. Andromeda is now in its quiet phase, an old, stable system waiting for its next transformation. In infrared images from modern observatories, the center of Andromeda glows softly, surrounded by a maze of dust lanes that spiral inward. These lanes act like rivers of material feeding the core. Over time, they will deliver enough gas to restart the black hole's feeding process. When that happens, the calm nucleus will awaken once more, and for a brief cosmic moment, the heart of Andromeda will shine again as it did long ago. The black hole at the center of Andromeda is not merely an endpoint of matter. It is a regulator, a timekeeper, a silent architect of structure. It reminds us that even at the largest scales, the universe is governed by balance, between light and darkness, between creation and collapse. It anchors the galaxy, holding its stars together while whispering the laws that shape them. Andromeda does not travel through space alone. Around it moves a retinue of smaller companions, faint dwarfs, irregular clouds of stars, and diffuse spheroids barely held together by gravity. They orbit like moons around a planet, tracing slow paths that take billions of years to complete. To the unaided eye, they are invisible. Through telescopes, they appear as small smudges on the edge of the great spiral's light. Yet together they reveal one of the fundamental truths of galactic evolution. Every large galaxy grows by consuming the small. The Milky Way has more than 50 known satellite galaxies. Andromeda has at least 40 and probably many more. The best known are M32 and M110, visible even in amateur telescopes as faint patches of light just outside Andromeda's disk. Each is a fossil of a larger system that Andromeda has stripped and reshaped. M32 is a compact elliptical, tiny, bright, and unusually dense. Its stars are packed into a region only a few thousand light-years across. Spectroscopic studies show that it once had a massive disk and extended halo, but those outer layers were torn away by Andromeda's gravity. Only its dense core survived. Today it orbits just outside the main spiral, moving at hundreds of kilometers per second, locked forever in Andromeda's grasp. The missing parts of M32 may now form part of Andromeda's own outer halo, dispersed so thinly that only their chemical fingerprints remain. M110 tells a different story. It is larger but more diffuse, stretched into an elongated shape by tidal forces. Dust lanes cross its faint disk, and in the infrared it glows with cool, aging stars. It too is being pulled apart. Slowly, almost imperceptibly, its outer layers are drifting toward Andromeda. In a few billion years, it will likely be absorbed completely. What we see today is a galaxy caught in the act of surrender. Beyond these visible companions lies a population of dwarfs so faint that some were discovered only within the last decade. The Pan-Andromeda Archaeological Survey, PANDAS, used wide-field imaging from the Canada-France-Hawaii telescope to map the region around M31 in unprecedented detail. It revealed dozens of ultra-faint galaxies and long stellar streams winding through the halo like ghostly rivers. Each stream is the remnant of a smaller galaxy torn apart by gravitational tides. As Andromeda pulled them in, their stars stretched into filaments thousands of light-years long. Some streams loop behind the galaxy, others cut across its face like scratches on a lens. Together they form a record of every collision Andromeda has endured. One of the most prominent features is the giant stellar stream, a ribbon of stars extending more than 300,000 light-years from the galaxy's center. Its discovery in 2001 offered direct proof that Andromeda is still consuming smaller systems. The stars within the stream are older and redder than those in the disk, suggesting they once belonged to a dwarf galaxy that fell into Andromeda about 2 billion years ago, likely the same event that created the thickened disk and ultraviolet rings seen today. The geometry of these satellites is striking. Many of them lie in a thin, rotating plane that stretches across hundreds of thousands of light-years. This arrangement, discovered in 2013, surprised astronomers. Dwarf galaxies around large spirals were expected to orbit in random orientations, but Andromeda's companions move in coordinated motion, as if they are fragments of a single structure. Simulations suggest they may have formed from the tidal debris of an even earlier merger, or they may trace a cosmic filament, a thread of dark matter along which galaxies are assembled. Either way, they hint at an organized history rather than chaos. Each satellite tells a story about Andromeda's appetite. Over billions of years, it has absorbed dozens of such dwarfs, growing larger with every meal. This process of galactic cannibalism is universal. The Milky Way does the same, currently dismantling the Sagittarius dwarf galaxy and pulling the Magellanic Clouds into distorted shapes. But Andromeda's evidence is clearer because it is viewed from outside. We can see the victim's remains written across its halo, faint arcs, loops, and shells glowing with the collective light of billions of orphaned stars. Chemical studies reinforce this picture. Spectra from these halo stars show a mix of elements heavier than helium, oxygen, magnesium, iron, all created in supernova explosions. The ratios of these elements reveal their origins. Some match Andromeda's own stellar populations, others bear distinct chemical signatures, marking them as immigrants from other galaxies. By comparing these patterns, astronomers can reconstruct when and how each merger occurred. It is a kind of cosmic archaeology, with chemistry as the tool and light as the evidence. Even the dark matter halo bears the fingerprints of this history. When a small galaxy merges with a larger one, Its dark matter is stripped and added to the host halo, altering its shape. Computer models that reproduce Andromeda's observed structure must include repeated mergers to match what we see. Without them, the galaxy's thick disk, extended halo, and numerous streams cannot be explained. Each edition of mass reshaped the gravitational landscape, preparing the system for its future interaction with the Milky Way. This constant cycle of consumption has consequences for the satellites that remain. Those on stable orbits may survive for billions of years, while others will spiral inward through a process known as dynamical friction. As they orbit, they stir the dark matter and gas around them, losing energy and momentum. Eventually, they sink toward the center, feeding the main galaxy just as asteroids feed the gravity wells of planets. Andromeda's future mergers are already underway, invisible, slow, but inevitable. In this grand pattern of growth, destruction becomes creation. The stars torn from a dwarf galaxy do not vanish. They join the halo, enriching it with metals and motion. Gas stripped from companions falls inward, fueling new rounds of star formation in the disk. Even the faintest fragments contribute to the luminous halo that now spans millions of light years. The act of consumption is also an act of renewal. Seen from afar, Andromeda's satellites form a kind of constellation, a miniature universe orbiting a single giant. Their interactions with the main galaxy reveal the same forces that shape the cosmos at every scale: gravity pulling, time erasing, and structure emerging from chaos. Each dwarf is a chapter in an unfinished story that leads toward the ultimate merger with the Milky Way. They are the smaller echoes of the fate awaiting both giants. As Andromeda continues its slow journey through the dark, it carries with it the memories of everything it has absorbed. The faint streams of light that lace its halo are its scars and its triumphs, reminders that even destruction in the universe serves a purpose. Through cannibalism, galaxies grow, diversify, and evolve. The night sky's brightest spiral is also its hungriest, and every glimmer around it is proof that nothing in the universe remains untouched by gravity's appetite. Look up on a clear, moonless night. If you live far from the lights of cities, you might see it, a faint, elongated glow high above the horizon. It does not flicker like a star. It does not move like a planet. It hangs quietly between Cassiopeia and Perseus, an island of pale light adrift in the dark. That blur is the Andromeda galaxy, our nearest spiral neighbor. What the eye perceives as a small smudge is, in truth, a vast city of 1 trillion suns. For generations, humans have stared at that blur without knowing what it was. Ancient astronomers recorded it as a mysterious cloud, a fixed point of faint light that never changed position. In the 10th century, the Persian astronomer Abd al-Rahman al-Sufi described it in his book of fixed stars, small cloud, in the constellation Andromeda. For nearly 1,000 years, that description stood. It was only in the early 20th century that we learned its true nature, that it lies far beyond the Milky Way, a separate galaxy unto itself. That revelation transformed our understanding of the universe. When Edwin Hubble measured the distance to Andromeda in 1923 using a variable star called a Cepheid, he proved that the Milky Way was not the entire universe. There were countless other galaxies, each a world of its own. That single discovery expanded the cosmos from one island to billions. And in that expansion, our sense of scale and meaning changed forever. Today, when we speak of Andromeda, we do not speak of mythology. We speak of a real structure, a collection of matter shaped by gravity, physics, and time. Yet, despite all our data, there is still something emotional about seeing it with our own eyes. Its light has traveled 2.5 million years to reach us. The photons that touch our retinas tonight began their journey when early humans were learning to use fire. They crossed the void between galaxies, untouched and unchanged, carrying the story of their origin across epochs of time. Through telescopes, Andromeda reveals itself in detail, a glowing core, sweeping arms, dust lanes curling like smoke. Long exposures show subtle colors, the golden light of old stars, the blue of newborn clusters, the red of hydrogen nebulae. In those colors, we see the life cycle of galaxies laid bare. Every hue is an age, every glimmer a memory of something that once lived and burned. The knowledge we now hold about Andromeda, its halo, its collisions, its approaching path, could make the universe feel distant or mechanical. But instead, it does the opposite. It draws us closer to the truth that we are part of the same structure. The atoms that make up our bodies, our air, our oceans were forged in ancient stars. Many of those stars were born in collisions not unlike the ones that shaped Andromeda. The same processes that govern its spiral arms govern the cells of our blood and the orbit of our planet. We are not observers of this universe. We are participants in it. In 4 billion years, long after Earth as we know it is gone, the Milky Way and Andromeda will meet. Our descendants, if they exist, may watch two galaxies merge in slow motion across their skies. They will see long arcs of light stretching from horizon to horizon, glowing trails of stars painting the night. What we call the end of our galaxy will be, for them, a beginning, the birth of a new one. It is humbling to think that the light we see from Andromeda today shows it as it was long before humanity existed. Every observation is a look backward in time. The Andromeda of this moment, the one truly existing now, is already slightly different. Its stars older, its paths shifted, its halo a little more entwined with ours. When we look at it, we see both history and prophecy, the echo of what has been and the prelude to what will come. Science gives us the measurements: distances, velocities, masses, temperatures. But beyond the numbers lies something deeper, the awareness of connection. We live on a small world orbiting an ordinary star on the edge of a galaxy. That galaxy is moving toward another, larger one, and together they are part of a cluster drifting through the expanding universe. Every element of that chain depends on gravity, the quiet force that links everything from atoms to galaxies. It binds the stars to their orbits, the planets to their suns, and the galaxies to one another. It is the same force that keeps our feet on the ground and draws Andromeda ever closer through the dark. When the first astronomers realized that Andromeda's light was blue-shifted, that it was coming toward us, they discovered something profound about motion on a cosmic scale. The universe expands, yet even within that expansion, gravity creates pockets of unity. Not everything drifts apart. Some things come together. Andromeda and the Milky Way are among those few. Their meeting will be a rare act of union in a cosmos otherwise pulling itself apart. From our vantage point, that future seems impossibly distant. But in the language of the universe, it is soon. 4 billion years is less than a third of the time the Milky Way has already existed. Everything that lives now, every ocean, mountain, and city, is a temporary shape within that larger unfolding story. And that story, written in light and motion, connects us to Andromeda as surely as it connects stars to their galaxies. Astronomers often describe galaxies as if they are alive. They grow, they feed, they evolve. And in a way they are. Each one is a self-regulating system, sustained by cycles of creation and destruction. Andromeda breathes in gas and dust, forms stars, and exhales energy and radiation. The Milky Way does the same. When they merge, their cycles will merge too. What will remain is not the death of two galaxies but the transformation into something new, a single, larger entity carrying the legacy of both. When we step outside and look toward the faint light of Andromeda, we are seeing that legacy in motion. We are watching the slow evolution of the universe, the same rhythm that created us. It is a reminder that even across 2.5 million light years, the connection between galaxies is real. The air we breathe, the atoms in our bones, and the light in our sky are all made from the same cosmic material. We are the continuation of processes that began billions of years ago in places like Andromeda's halo and its forgotten stars. The Andromeda galaxy is not just a distant object. It is a mirror. It shows us the structure of our own home, the fate of our future, and the scale of our place in the universe. Its light is ancient, but its meaning is immediate, a bridge between science and wonder. So, when you next look at that faint smudge of light in the night sky, remember what it represents. It is not just another galaxy. It is the beginning of a story that has no end, a story written in gravity and time, shared by two galaxies destined to become one. And in that story, we are not bystanders. We are part of the same unfolding chapter. A small consciousness aware of the vast universe that made it, standing on a tiny world, looking up at a neighbor already reaching out across the stars.